Section 22.15, Carbenes. Carbenes may exist in the singlet or triplet electronic state. Singlet carbenes have an electron spin quantum number of 0, with 0 unpaired electrons. Triplet carbenes have 2 unpaired electrons. They can be alpha-alpha, beta-beta, or alpha-beta plus beta-alpha. They correspond to M sub s being -1, 0, or 1. And therefore, we have this spin quantum number S, uppercase S, is equal to 1. Now let's look at a few pictures of the singlet carbenes and triplet carbenes. So over here, this is a singlet carbene. We have 2 functional groups, and this lone pair electrons. 1, 2, 3. This 3, 2 bonds plus this lone pair, are sp2 hybridization. So this carbon also has a empty p orbital perpendicular to the sp2 plane. This picture is similar to this picture. It's just you need to move 1 electron to here and flip its spin. Now we have 2 alpha electrons in this triplet structure. Again, sp2 hybridization, but only 1 electron occupies this sp2 hybrid orbital. Another electron occupies the p orbital that's perpendicular to the sp2. This is a different triplet structure. In this structure, we have sp hybridization. The center carbon is bonded to 2 different functional groups with a bond order of 180 degrees. And that tells us this is sp hybridization. This carbon has 2 other p orbitals, each occupied by 1 electron with the same spin. Now let's get back to this singlet carbene. The electron pair over here may become the sigma bonding electrons in a transition metal complex. And meanwhile, if you look at this carbene structure, it has an empty p orbital here, which can accept the electrons from the metal. That results in a double bond between the metal and the carbene, and this is very stable. This is called a Fischer carbene. Again, 1 sigma bond with electrons donated by this carbene, singlet carbene. And also there's a pi bond. If the transition metal has d electrons to donate, it may donate d electrons. Or you can say delocalize this d electrons into this empty p orbital centered on the carbon in this singlet carbene. And that's why you have a double bond between this carbene and the transition metal. There are ways to stabilize carbene structures because, look, there's a empty p orbital on this carbon, right? And if there are lone pair electrons from the neighboring atoms, for example, nitrogen atom, those lone pair electrons may flow into this empty p orbital. That will lower the electron-electron repulsion and stabilizes this singlet carbene. So sometimes we can have very stable carbene by allowing electrons to flow from neighboring atoms to the empty orbital of the carbon. In a triplet carbene, the 2 unpaired electrons adopt the same spin. The triplet carbene often has lower energy than the corresponding singlet carbene because of the lower electron-electron repulsion. You need to pair up the 2 electrons in the same orbital in a singlet carbene. So very often the electron-electron repulsion is slightly greater in the singlet carbene. And also in a triplet carbene, there's more negative exchange energy. Well, this is because electrons with the same spin can better avoid each other than electrons with opposite spins. So if we look at the triplet carbene structure, electronic structure right here, so you can tell that a triplet carbene potentially can form two bonds, 1, 2, with two different transition metal centers. So one here and one here.